This is the law of reflection, the shortest law of physics you will ever learn. When light hits the surface and reflects off it, it reflects off the surface at the exact same angle that it hit, as you can see both on the front surface and on the back one. The angle in, also known here as the angle of incidence, you can call it theta in for short, is going to be exactly equal to the angle of reflection on the other side. See? Just like this. Angle in, angle out. Same thing. At this point in the unit, we're going to get into good habits. We're going to draw a line perpendicular to the surface we're working with. That's called the normal. The angle of incidence and the angle of reflection is measured from the normal, not from the edge of the object itself. Get used to working with the normal. You'll need it for everything else you do with light, rays, waves, and optics. Why do we use the normal? Because surfaces in the real world aren't always as perfect as the surfaces you draw on paper. See? In theory, everything is as smooth. I'd say as smooth as glass, but real glass isn't actually that smooth. Feel it with your fingers. Take a microscope to the surface and you will see that the whole surface is covered with bugs. Get down to the molecular level, everything is going to be bumpy. Sure, when you hit the surface, the angle in equals the angle out. But if you didn't correctly see which angle you hit the surface, if you thought the surface is absolutely flat, and it turns out you hit some weird funny bump over here, the angle in was a lot smaller than you thought. The angle out is going to be a lot smaller too. Light scatters off all surfaces, all the more so if they are rough. We call this diffuse reflection, because if the light hits something that's rough all over the place, there's hardly going to be an angle anywhere where there isn't some funny bump going around, with the result that the light diffuses all over the place, just like this. It scatters everywhere. We see things when light enters our eyes. If the light ray doesn't reach our eyes, if it goes somewhere else, over our heads or under them, we don't see it. Mainly, we see objects because they have rough surfaces. Light scatters off of them in all directions, as this bumpy surface reflects the light in all directions. Some of the light gets into our eyes, and so we see. What does this look like? It looks like a reflection. See? Angle in equals angle out. But in the mirror, it looks like there are 4 rays, not 2. Let's look again. See? It looks like this one is going straight across. Try it at another angle. Straight across. We know there isn't any light coming from that side of the mirror. The reflection makes it look like there is. Light travels in straight lines. We spent the first 3 to 5 months of our existence as infants trying to figure out where things were. And one of the first things we learned, along with binocular vision in depth, is if you reach out for it straight out, eventually you'll touch it. Our brains know that light travels in straight lines. They're not going to be reprogrammed at this late date. So when we see light coming this way, our brains just assume there's only one logical place for that light to come, and that's from that way. We see the light as if it were behind the mirror on the other side, coming from a straight line path. Look at the distances. You'll see that in flat mirrors, the reflection looks exactly the way it does in real life. Same size, same distance, because light's coming at the same angle. This is way cool with more than one mirror. You can see the objects reflected multiple times as the light rays move outward in straight line paths, hit one mirror, reflect off that mirror, and then hit the other one and reflect off that one too. With multiple mirrors, you'll see multiple images, each one at the same angle. If you trace out all the rays, it looks something like this. Draw your ray of light, draw a normal here to the surface, and reflect the light at the same angle on the other side of the normal. Notice it's scheduled to hit the next mirror. Also notice you do have to do this with a ruler or a straight edge. Light travels in straight lines. If your line isn't straight, then your diagram will have absolutely no correspondence with life in the real universe around you. Keep tracing. You'll see where the light rays go. Now, according to your brain, where are the light rays coming from? This light ray seems to have come from this way. This light ray seems to have come from this way. That means there must be an image over here. Similarly, these 2 light rays look like they came from that way, making an image over here. Conclusion? you'll see two other images in the mirror in addition to the one you expected to see. Pretty cool, huh? Try this one in your note packet with a ruler or a straight edge. Practice drawing normals. Practice seeing at which angle will the light reflect and what will it hit if it does. Trace out your rays and see where the images are going to come. We will set up the mirrors in class and try it when you get back. Happy ray tracing!